All right, we're going to pick up the second half of the wedge or the diffusion fish walkthrough. In this video, we're going to be focusing on the setup and solution, as well as implementing the parameterization. The previous video, if you haven't already gone through, discusses the generation of the geometry as well as the mesh. So let's go ahead and fire up Fluent. We're going to use a double precision, and for our VMware machines, we're going to use 4 processors and go ahead and start this up. So the simulation setup itself is actually pretty similar. We're going to have a very slow flow. We're going to have a 1 millimeter per second flow coming into our inlet. Free slip boundary conditions are on the side, no slip boundary conditions along the wedge itself, and then an outlet boundary condition. We're going to do just a steady state simulation, and the viscosity model that we're going to use is a laminar viscosity because we're operating in a relatively low Reynolds number. So the setup is relatively simple. We're going to create 2 variable outputs or 2 report variables that we're going to be both outputting to files as well as outputting to our parameter evaluation. So nothing that we have to do for our general. Pressure based is fine. Steady state is fine. Go into our model. And this is where we're going to set our viscosity model to the laminar case. There we go. Set that to laminar, and we're good to go. We'll go ahead and load up our water. So we can go to Fluent Database, scroll all the way down to water liquid. We'll copy that, and that's entered into our fluid options. We're going to set our fluid domain to water. Okay. Now we're on to our boundary conditions. So our inlet boundary condition, we're going to set this velocity magnitude to be 0.001 or 1 millimeter per second. Outlet, no modifications are needed. For our walls, for our free slip walls, we're going to specify our shear values to be 0. No need to change anything on the no slip walls, but just to verify, these are stationary walls with no slip boundary condition. Okay, so that takes care of our boundary conditions. All right. Now we're going to go ahead and create our 2 new report definitions. So they're both going to be force calculations related to drag. So our first one, we're going to name report def drag coef for coefficient, and we're going to be calculating that on our no-slip walls. We're going to go ahead and click on this create output parameter. This will allow us to evaluate how this parameter changes as the slope angle changes. And we can go ahead and click OK. And we're going to create a second drag variable. This time we're going to call this one drag force. We're going to be calculating the force on the no-slip walls. And for this one as well, we're going to go ahead and turn on our output parameter. Okay. We can close this down. For our monitors, first we're going to set our residuals everywhere to be 10 to the minus 4. So we're going to just add a 0 for all 4 of these. Okay. We're going to create a report file where we're going to now output our coefficient and drag forces into our file. We're going to call this drag data, and we'll output the values for every iteration. Okay, and close this down. All right, we can go ahead and initialize. We'll use the hybrid initialization, it's fine. Okay, and let's go ahead and create our contour plot. So our contour plot, we're going to plot up our velocity field. Velocity magnitude is fine. The issue now is what slices or what projection of data should we show. So if we just do this, we can save and display. We don't really know what surface we want to plot. So if we pick any of these surfaces, it's going to sort of show us a solid color, which isn't overly informative. Especially since you can imagine that our no-slip boundary conditions along the wall of the wedge don't really have any color variation either. So instead, what we're going to do is we're going to create two new surfaces. So we're going to click New Surface, and we're going to be creating two planes. So we're going to create the XY, or the ZX, as well as the XY plane. And we're going to plot our velocity profiles on those two planes. So we can see cross sections of our wedge. So you can sort of see this is a top-down view, and this would be a side view of our wedge. It might be helpful to go ahead and plot the no-slip walls as well. So now you can see your blue wedge showing up, but I don't really know if that's going to tell us a whole lot, so we're going to just turn that one off. Okay, we're going to rename this contour vel. Save and display, and close. Now, you can go ahead and create an animation of the velocity profile. Again, we're doing steady state, so there's not going to be too much evolution of this profile. But in the parameter variation testing that I did earlier, it was kicking back an error. So we're going to not go ahead and turn on that calculation activity, and we're going to go just straight into the run calculation. So run calculation for 100 iterations. We're going to output values every 20 iterations. And we're going to go ahead and calculate. So the startup time for the calculation takes a little bit of time, but once the calculation gets started, it doesn't actually take too many iterations. So in the past, it's taken about 60 iterations to reach convergence, and so hopefully that'll be the same this time as well as for your simulations. Okay, so calculation has started up. So again, we're trying to get everything down to the 10 to the minus 4 levels. So at this point, our 3 velocity components have converged, and our continuity residual is also getting pretty low as well. And so at this next update, we should have reached convergence, which is good. Okay, and then we can go ahead and display our velocity field again. And we get what we would expect. In the far field, we have pretty close to the inlet velocity, so pretty close to that 0.1 or 1 millimeter per second velocity. Close to the edges of the wedge itself, we get a blue, which corresponds to roughly 0 velocity. And then we get a green boundary layer that grows and pretty quickly becomes sort of the full far field velocity itself. This is a nice side view of the wedge, and then a top-down view shows that we get a similar boundary layer development along the sides, and then the wake behind it is relatively small. Okay. So that finishes the calculation itself. We can go ahead and save the project. And now we can start thinking a little bit about the parameterization. Okay. So back into our workbench, we now see we've sort of got the completion of this control loop. So we have some parameters input and then parameters output. So let's go ahead and click on parameter set, and that pulls up a new field for us to look at. And so this range here shows us the data points that we've evaluated so far. So the first one, our slope angle, so that was that parameter we set earlier, has a value of 10 degrees. Our drag coefficient, that's the report output that we created, has a value of 3 times 10 to the minus 6. Our drag force is about 1.8 times 10 to the minus 6. And what we're going to do is, for now, we're going to add one more parameter variation. So let's go ahead and add a value of, let's say, 2.5 degrees. Okay. We're going to click retain, which is going to retain the files that are necessary to run this simulation. And we're going to go ahead and right click and set as current. And so what that does, it's going to take a moment to do that. What that does is now we can go back into our project and see all these values are now no longer up to date. And so we can go through and update them, or we can have the parameterization try to do the update for us. So we're going to do update selected design point. And we're going to track the output information down here in our progress bar. And if this is working correctly, what it should go through is, starting at the very beginning of the simulation where we created our geometry, it will modify that angle to be 2.5 degrees from the slope to the x-axis, so a total slope angle at the tip of 5 degrees. It'll update the geometry and go through and try to update the mesh accordingly without changing any of the properties that we've set, and then update finally the solver, and then potentially try to solve the problem. Now, there are instances where this breaks down a little bit, so the nice thing is when we do retain the information, we can go through and just check in to see, okay, did the geometry get updated appropriately? Did the mesh look right? Did the solver work? So right now we're in the updating setup part, so it's already completed the geometry in the mesh. Maybe take a look over here. So yep, you can see our geometry and mesh have been updated, our setup's been updated, so now it's trying to figure out, can it solve it on its own? So sometimes it does, sometimes it doesn't. In the event that it doesn't, we can go through and actually open up the solver and go ahead and run the simulation ourselves. So now we're in the solving phase. It's updating the solution. So we may have successfully gotten our results. Okay, so it was successful. So if we look now into our grid, our 2.5 degree slope angle has decreased our drag coefficient from about 3 times 10 to the minus 6 to about 2 times 10 to the minus 6. And our drag force has also dropped from about 1.8 to about 1.2 times 10 to the minus 6. So what you'll do in the homework is you'll go ahead and make a different parameter modification and evaluate what happens as you change two different parameters in terms of its impact on your drag force.